via paper. So I will be in this room. We'll be having the exam per our normal class schedule. You can take it either on campus in this room, or if you're allowed to be off campus, off campus, or on paper. Okay? Now, one other thing with exams. This is going to be another learning experience among many that we're going to have this term. Normally with exams, guys, I bring in some kind of food for the class because I feel that the condemned deserve a last meal. Unfortunately, that's probably not a good idea. What I'm going to do is, I'll see if I can find something sealed, like individual packs sealed. If you want to bring in your own snack, that's fine. Unfortunately, as I said, I really like to bring in food and I can't, other than sealed. If anybody has any dietary restrictions, feel free to let me know, because it'll probably be something horrible like sealed packages of cookies or chips or something like that. And if you'd rather not have that, just let me know. Okay, any immediate questions on the exam? Yes?
We come in, we have a hard count here, so it's just all on campus.
I will have it available on Canvas. I will also have hard copies if you prefer to take it on hard copy.
How does it work being online? Is there a time limit? You start late by a certain time?
There will be a time limit, same time limit that we will have in class.
Okay.
So it'll be online. The content will be as close to identical as I can make it. I would ask that if you're going to take it online, don't take one of the hard copies. Feel free to use your own scratch paper, though, if you wish some.
And can we sign in Zoom during the class period and if there's questions, take it that way?
Yes, I will have Zoom up and running during the class period.
Okay.
I probably won't post that video, though, because it'd be really boring.
Okay. And one other thing, as far as formulas, will we have a formula sheet, like for example, like the PQRS, or do we need to memorize those formulas?
Trying to decide if I want to have fun with this question or not. And the answer is I don't want to have fun with it. My tests are open book, open note. There's a very specific reason for that, guys. Let's see. Who's anybody in here younger than a junior? No? Okay, 2 years from now, you're going to be graduated and working, right? It's going to be awesome. Do you think your boss is going to come to you and say, hey, I need you to solve this problem? By the way, closed book, closed notes. It's not realistic. That is not how engineering is done. We're here to teach you how to apply information. Some things are best put into your memory, and I trust you to do that. Some things you're always going to be able to look up. Other questions?
So the exam, for the online people, we will look at the exam and do the exam, then we will look at the campus, or
It will be an interactive exam on Canvas.
okay, so we'll scan it and we will submit it.
No, it will be an interactive exam on Canvas. So you will be able to work out the problems on your own scratch paper, enter your answer. I will also have an assignment open so that you can send me pictures of your scratch sheets if you wish for partial credit. But you'll be answering on Canvas. Clear enough? Yes.
When you say open book, open note, can we have like our laptops open with the slides and things, or?
You can have your laptops open with the slides. I will be wandering around just to make you nervous. And also maybe to make sure you're not using Google or something fun like that. Your slides are part of your notes, so they're available to you. Any other questions?
For the graphical methodology, will be the exam, the graphical method that the class was
video on YouTube. Generally, Bashar, the way that I attack these things is, I'm going to give you a problem. Unless I tell you to use a specific method, I don't care which method you use. Okay? So if I post a problem, I'm likely not to tell you which method to use. You can use whichever one you prefer.
Where can I find that video explanation of the graph method? I missed that.
It is posted, there's a link to it posted in the module for, I believe, last week.
Okay.
And the best thing is you can fast forward it.
Great.
Any other questions? All right. Let's get on with the show. All right. So today we're going to be covering a portion of Chapter 6. We'll be completing what we're going to be doing in Chapter 6. There's some homework problems that are posted. A couple of these I have posted solutions to up on Canvas, so you can go through those as well. If you do have any questions, I would strongly suggest, advise, that you feel free to contact me, either email or if it's really an interactive question, we can set up a separate Zoom. So don't hesitate, guys, okay? All right. So, when we finished up last time, we were looking at graphical techniques to do velocity analysis. Tonight we're going to look at analytical techniques. But first, a couple of things to talk about that are mentioned in your book and that I would be remiss in not stating to you. We talked a little bit about that velocity. Now let's talk a little bit about power. Power is something that we are going to be very, very interested in throughout our engineering lives, because power is how we do things, right? From a linear standpoint, we can see power is equal to the product of a force and a velocity. And using those techniques that we talked about for dimensional analysis, you can see the underlying units that make up power. From an angular standpoint, which is even somewhat more common in mechanical engineering, power is equal to torque times angular velocity, or speed. So this is a really important thing to remember, guys. This is probably one of the most important things that you're going to hopefully take away from this class. Or, if we look at SI units, Newton meters, radians per second, so Newton meters per second. We're going to use this a lot. I will suggest to you that the reason this is so important is it's going to be used throughout your engineering careers. Now, we're all, I think everybody in this class has probably already had the basic circuits electronics class, right? Yes? So, no? Ooh, good, we're going to learn something else today. So, for electrical power, what is that equation? Power is equal to what, electrically?
Current times voltage.
What was that?
Current times voltage.
Current times voltage. What else? Is there another term in electrical for power? Some other equation?
Current squared times resistance.
Current squared times resistance, right. And in engineering, guys, you're never going to be far off, you're never going to go far wrong if your analysis of a problem begins with power balance or energy balance. You've probably heard this in other courses too, with thermo and other things. Same thing goes here. And for us, in this class, kinematics and dynamics of machines, mechanical power is torque times speed. And if we're trying to equate this with electrical power, which becomes pretty common as you go into mechatronics, hybrid vehicles, into any electrically actuated machine, you're going to want to look at the power in versus the power out. Okay? Very important relationship. Probably hammered on it a little too much, but a little too much is probably not bad at this point. When we look at these things right now, and just in general, you're probably going to look at them ideally. So you're going to assume 0 losses. This gives us rise then to a couple of terms that you might run across in literature. The torque ratio, so the torque out divided by the torque in. Or the mechanical advantage. Mechanical advantage we use a lot in devices that take a small input power and give us a small output power, but multiply something about it. Who has a multi-speed bicycle? How many speeds does it have?
I guess 7 gears.
7 gears, okay. And in first gear, do you pedal really fast or really slow to go into speed?
Really slow.
Really, in first gear?
I haven't ridden my bike in a while.
Okay.
It's probably really fast.
Really, really fast. And in 7th gear, if you pedal at that same speed, how fast are you going?
Not very.
No?
Well, if you're pedaling already, then you're already.
Yeah, you're going fast, fast. What you're doing is trading torque for speed. At low gears, you're pedaling like crazy and not putting in a whole lot of force on the pedals, right? You're not putting in a whole lot of torque. It's being multiplied back to the rear wheel. At a higher gear, you're pedaling slowly, but it's hard to pedal. Trading torque for speed. Okay. Now, we talked a little bit about this last time. I'm just going to kind of glom over this a bit. It's generally not a huge topic. So I'm giving you a couple of things to look at on your own. Centroids versus velocity of slip. We talked about instantaneous centers of motion last time, remember? Centroid, instantaneous center of motion. This is something where you've got an instant center that your links are revolving around. And that center always changes. Forms a path that we call centroid. This is used for things like non-circular gears, or a good rocking chair actually is a changing centroid in order to get a smooth rock motion. I more want to mention this than anything else. It's not something we're going to hit hard in this class, but it's worth a look through, guys. So take a look at figure 614, and you can thumb through these two examples. Don't spend a whole lot of time on them. Okay, now let's get to the meat. We looked at a graphical technique to do velocity analysis. This is going to be an analytical solution. Specifically right now, this is for a 4-bar linkage, pin jointed, so it's got revolute joints at each of these intersections between the links. Here's how we go about developing the equations to do this. Just like we did with the dot product method for position, or with some of the things we've looked at velocity-wise with vectors, we're going to define each of these links as a vector. And we're going to give them directions such that when we add them up, it's still going to be equal to 0. All right? That's where all of these vector methods come from for kinematics and dynamics of machines. We're also then going to say if we take these vectors, we can define these in terms of the Euler identity. You can look back in previous notes for this. If we take the Euler identity, this is position, it's stated as position, and then we differentiate our position with respect to time, we get an equation that looks like this. This is actually kind of helpful. If we're trying to find velocities, this equation has the angular velocity of all three moving links in it. As soon as we get an equation that has the quantities we're searching for, that gives us opportunity to manipulate things and come up with a way to determine them. From the graphical analysis that we already did, we know that the velocity of point A on link A or R2, depending on which identification you're using or the book is using, that velocity can be seen as omega 2, the angular velocity of that link, multiplied by its length. The j and e raised to the j theta 2, that gives us the direction of the velocity vector. The magnitude is just the length multiplied by the angular velocity. Similarly, for the velocity of b with respect to a, remember, when we're saying with respect, that means we're looking at the velocity of point B, assuming that point A is stationary. That magnitude is still going to be equal to the length of the link, B, multiplied by its angular velocity, omega 3. And the same thing for the velocity of B with respect to the ground. We're just changing which angular velocity we are using. If we rearrange that, and assuming that we know the position of this linkage, we can generate then fairly simple equations describing the angular velocity of those links. Now, single degree of freedom mechanism. So there are two things here that we need. For a single degree of freedom mechanism, we need to know the positions. If we know the position of one, we can find the position of the others. And we need to know the velocity of one so that we can find the other two. Okay? This leads always to a great question about the content of the test. Does anybody see the link here and the question that comes up? No? Should I just tell you? Everybody just too nervous about the test? Yep, okay, that's a good answer, fair answer. So, do we have to find the positions and then find the velocities? Because if I screw one up, then I miss the whole problem, right? Who's thinking that? Who's thinking it now? That's terrifying, isn't it? I usually break the problems up. I don't want you to have a cascading failure all the way through the test, because it's ugly and I don't want to see any of you cry. Usually don't want to see any of you cry. So we won't do that. Point is that if we know the position and we know one velocity, we can calculate the others. Let's try this out. Example 6-7 on page 323 in your book. Let's see here. I don't think I want to do that. People online, can you see the camera okay? Yes? No? Maybe? Okay. Just remember, I'm going to be posting another video that should show a better view, so don't freak out too much. All right. Let's try 6-7. this harkens back to example 4-1. On page 194 in your book. And this is for a 4-bar linkage, guys. This is what we're shown or told about the 4-bar linkage. Link D is 100 millimeters in length. Link A is 40. B is 120. And C is 80. We're also told that theta 2, so the position of link A is 40 degrees from the horizontal. And from the example, we're told the following, that, let's see, which one do I want to do? Well, that's one possibility. I'm just going to do, well, maybe we'll do all of them. Why not? So theta 3, 1 and 2 were 20.3 degrees and negative 60.99. Theta 4, 1, 2, negative 98.1, and 57.3. All right. So, solution techniques. We haven't talked about solution techniques too much. I'm going to always give you the most important 2 steps. The first step is don't panic. The second step is start with something easy. In this instance, guys, what you should always start with, and really for almost any problem in KDM, is create a little sketch of your system. Get a feel for what it looks like. It helps you to determine whether or not your answers are sensible. So let's do that. I'm not going to create it dimensionally. I'm just going to draw something that is roughly the size that I'm going to care about. So my fixed length is 100, 40, 120, 80. I'm going to draw something that's some length. And I will call this my fixed length. I know that my crank is 40 millimeters at about 40 degrees, so I'm going to draw something a little bit less than half that, and something like 40 degrees. My coupler is long, it's 120. And my my rocker is also pretty long, 80. So I'm going to just kind of eyeball it and say it's probably something like that. It's not exact, but it's enough to give me a feel for what my system looks like. I'm also going to make a play that's very, very important, which is generate more information about it. Why? Number one, it's easy. Get you past the first thought of, oh my God, how do I do this? Also, in context of tests, it says, ooh, partial credit. Why wouldn't you? So, let's see here. These links, regarding their length, say anything? What kind of linkage is this?
This is a prime market time rocker mechanism.
It is indeed. So it's a crank rocker. That means that the long plus the short is less than or equal to the length of the other two links, right?
So A is the short of the situation, and theta 2 is the enter to the mechanism.
That is accurate.
Theta 4 is the output of the mechanism. Theta 4.
Theta 4 is going to be, should be,
The output of the mechanism.
correct. And this is
Theta 3.
theta 3. So, it's a crank rocker. We know it's a crank rocker because A is the shortest. We can amuse ourselves and say 160 is less than 180, so it is a crash-off mechanism. Great. So we know more about it, right? Now, the beauty of this analytical technique is that it's plug and chug. So for this particular problem, all we need to do is remember where to find our equations. We also need one other thing. So omega 3 is equal to omega 2, A times omega 2 times the sine of theta 4 minus theta 2 divided by B times the sine of theta 3 minus theta 4. Now, single degree of freedom mechanism, so we need to know the angular velocity of one link. It's generally going to be given as omega 2. I didn't write it down, but I should have. Omega 2 is equal to 25 radians per second. So now it's just kind of plug and chug, right? We choose two of our values, preferably two that go together, for theta 3 and theta 4. Plug it into the equation. We can calculate then omega 3. Omega 4 is similarly simple. A times omega sub 2 sine of theta 2 minus theta 3 divided by C multiplied by the sine of theta 4 minus theta 3. Now what if some joker decides to throw you a bit of an issue? What if we said, instead of omega 2 is equal to 25 radians per second, what if some joker instead said, hey guys, the velocity of A is equal to 1,000 millimeters per second. What would we do?
So here equal R, del omega equal R theta. So E equal W omega R.
Bashar, you're too fast. I'm trying to make people worried.
Absolutely.
That's okay. So guys, I don't know if you could hear Bashar very well. He's quick on the draw. In this instance, hopefully remind you that the velocity is equal to omega r, right? So we could solve for omega. Yes, maybe. Okay. Okay. So, anybody want to try one of these just to see what you get for fun? We'll use 57.3 and 20.3 are the ones that go together. Everybody finish your calculations?
Omega 3 is negative 4.12,
Yep.
and omega 4 is about 7.
Yes. So, physically, kind of what does that mean? Let's go ahead and just modify this to match. Here's package. So told that crank moves at 40 millimeters per second. Let's do that. And it's positive rotation, so that means in plane, this thing is moving counterclockwise. From the geometry, guys, of a crank rocker, get this front light to make it a little better. So from the geometry of the crank rocker, it's really easy to see that the rocker is going to have the same sign of angular rotation that the crank does, right? In most cases, the sign of the coupler's rotation is going to be the opposite, and its magnitude is going to be quite a bit lower. So that's one pattern you want to kind of keep an eye out for. It's a good way to get a feel for, have I screwed this up? Now, that's for a 4-bar length. We've looked at a couple of other mechanisms, so we'll take a look at those. The crank slider and the slider crank. Anybody remember what the difference between the crank slider and the slider crank is?
Is the offset? Offset is the front.
No. Good guess. The crank slider, in the terminology used by your book, means that you're driving the crank. That's what drives the mechanism. Slider crank, you're driving the slider. So slider crank would be something like an internal combustion engine being driven by the explosion of the fuel-air mixture. Crank slider would be something like, say, a reciprocating pump. You're driving crank. So very, very similar, but your known item will be different. For a crank slider, you're usually going to know omega 2. So this is, in concept, very, very similar to the 4-bar length. We can look at section 4.6 if you're curious for the position equation, but same thing. We would take the position equation for this linkage in vector form and differentiate it. Substitute in the Euler identity and simplify it, and we would come up with this equation, tying in the angular velocity of the crank to determine the angular velocity of the connecting rod and the linear velocity of the slider. The way that the Euler identity works, it breaks it up into 2 components. Your book likes to call them real and imaginary. I like to call them x-axis and y-axis, because we're working in a plane. But these 2 things, the x component and the y component, for these single degree of freedom mechanisms operating in the plane, they are independent of one another. What that means is that all of my y component velocities need to sum to 0. All of my x component velocities need to sum to 0, independently of each other. It simplifies the way you can set up the problem. So, if we crunch through that, we actually end up with 2 very, very simple equations to get omega 3 in terms of omega 2, and to get the velocity of the slider in terms of omega 2 and omega 3. There is an example for this in the book. In the interests of our pandemic, I probably won't go through it just because it's pretty simple. See, these equations are really simple. Unless you want to go through it. Would you like to? So a slight no. You guys are a tough audience tonight. I can't see any smiles or smirks. Maybe a couple. Will it be on the exam? It's a good question. Any problem like this could be on the exam. Does that change your answer? Do we want to go through it, guys, or no?
Sure, let's do it.
Sure, okay. Let's do it. Sounds like fun. So this is on page 326. So this is a crank slider. As I said, it's on page 326. This is example 6-8. And we're told the following, that our crank, A, is 40 millimeters in length. Our connecting rod, B, is 120 millimeters. Our offset, C, is -20. The crank position at the time of interest is 60 degrees, and the crank velocity, omega sub 2, is -30 radians per second. All right, so step number 1, don't panic. Step number 2, do something easy. What we want to find will be omega 3, velocity of point A, and the velocity of point B. So, along with our don't panic strategy and with doing something easy, let's draw a picture of this. It's a crank slider. Not going to bother making it dimensionally accurate, just close enough to get a good feel for it. So, I know that my crank is 40 millimeters and it's at an angle of 60 degrees. How's that look? Just like you would have drawn? If you were on a chalkboard with a tiny piece of chalk? Yeah? Okay? Our offset is -20. So the slider path is parallel to our x-axis, but it's 20 millimeters below it. Our con rod is 120, so it's long. There we go. Label my points. Label my links. And maybe give a nice dotted path for my slider. So it looks like this. My equations are pretty easy. You calculate omega sub 3 as being equal to A multiplied by the cosine of theta 2 divided by B multiplied by the cosine of theta 3, whole mess multiplied by omega sub 2. Oh no! What's theta 3? It's not given. Oh no, what are we going to do now? So, I see two possibilities. 3. Yeah, Bashar, you're still too fast on the uptake. I'm trying to frighten my students.
I'm sorry.
That's okay. So what do we do? When in danger or in doubt, run in circles, scream and shout. Yes? No? Don't panic? Yes? No. No, let's not panic. Guys, there are a couple of ways to solve this. First off, very quickly, on a test, same thing applies. I'm generally not going to give you a problem where you need to both calculate the position and then the speed, because it's too fraught with difficulties. If you screw up one, you're going to get the rest of the problem wrong and you've blown your whole test. And it doesn't really tell me whether you knew how to calculate the speed. So two other ways to attack this. We could go back into the position analysis for crank sliders. That's in your notes. It's not hard to do. Or, this is kind of a pretty easy trigonometry problem. Which one should you use? What do you think? Nobody want to get there? Trigonometry? Yeah, that's what I would do. Unless your sadistic teacher tells you to do it a different way. Since I'm not tremendously sadistic, I probably won't. Because I only test you on one thing at a time on a problem. So, if we were to do trigonometry, what we would find is that in this particular position, our theta 3 is 152.9 degrees. It can also be something else. There are two possibilities. In the other position, theta 3 would be 27.1 degrees. Usually I will make it pretty explicit which position I want you to calculate in. So now we have A, B, theta 2, theta 3, omega 2, and this becomes an engineering student dream, right? Plug and chug, piece of cake. The main thing to do is don't panic. Similarly, we can calculate the velocity of the slider. This is equal to negative A multiplied by omega 2 multiplied by the sine of theta 2 plus B multiplied by omega 3 multiplied by the sine of theta 3. Easy peasy, right? So velocity analysis analytically is really, really easy. The only tough part is making sure you have the positions and making sure you can find the formulas in the notes or you remember them. That's great for a test, so that's one way to approach it. 5 years from now, you're probably not going to remember that equation. That's why we also learn the graphical method. Questions on this one? No questions on this one? No? How do we get the theta 3? There are a couple of different possibilities. Look at the camera again. So here's theta 3. We've got this angle. Can you see what I'm drawing on the board? You've got this angle, so that means you can calculate this length, right? And we have the offset, so we can calculate this length. So that means we can calculate this angle. And once we have this angle, this one's trivial, right? That's one way to do it. Very, very easy trigonometry problem. Not a problem. Other questions? Okay. Now, a slider crank is pretty much the same thing. Same basic generation of the equations, just driven by the slider. You can get the position equation in section 4.7. And that allows us then to solve for what we don't know, given the velocity of the slider. There is This one, 803. I'm happy to go through it, but it's really just plugging and chugging. Now, I would rather you get out a little earlier too. 4-bar inverted crank slider. This one I gave you as section 4.8 for student review. I just wanted to touch on it so that we have the equations in your notes, just because it's easier to find it in the notes than it is in the book. Okay? Now, we have looked at the position of 5-bar geared 5-bar linkages before. So we should also note that this same technique works for calculating the velocities of such a beast. We get our position equation, take the first derivative of it, using the Euler identity for the equivalence. We remember that omega sub 5 is related to omega sub 2 by the gear ratio. And that allows us to come up with these really nasty looking but actually pretty easy equations for velocity of geared 5-bar link. So this technique will work with any mechanism you can dream up. Get an equation for the position, differentiate it, substitute in the Euler identities, manipulate it. It just gets harder with more complex mechanisms. Enough so that at this point, most practicing engineers will use motion simulation software instead of going through and driving the equations. Because again, 5 years from now, we don't remember it. However, you can use the graphical velocity analysis techniques on this beast too. And they will still work just fine. And that is a method you can remember. So that's why we taught it. All right. So finishing up the new material that will be on the test. Velocity at any point of a linkage. Once we know the angular velocities of these links, guys, we can calculate their linear velocities anywhere, any point on those links. We'll start it very, very simply. If I look at what we've been calling link A, in this case, and this is probably worth stating, the author of your book loves to do this, so we're going to have to get used to it. We've substituted in this big triangular piece for the nice simple link. This triangle moves as one. The velocity at point S can be calculated since we know the angular velocity of that whole link. It's just going to be the sum of its components in each direction in the plane. We can do the same thing with a point on this link or this link. It's pretty easy to do. The main thing to do is remember the all-important equation that V is equal to omega R. And R is just the distance from your point of reference to the point of interest. One more thing, just to see if you guys have been listening and remember this very vital thing that we talked about previously. So let's say I've got 4-bar link like this. Okay. And This is omega 2. What can you tell me about the direction of the linear velocity of point A? There's a specific word that I wanted you to associate with it. Hey, you guys are brilliant. That's great. What about the direction of the relative velocity of B with respect to point A? Perpendicular. What about the velocity of point B with respect to this length? Perpendicular. So that's one of those things that if you remember about linkages, will stand you in good stead to try and figure things out and make sure your answers make sense. The velocity between any 2 points, the relative velocity, is always perpendicular to the straight line between them. Okay? And that is all I have for you today. Questions? All right. I'm not sending you with any homework because you've got a test to study for. I will be watching for questions. If you have any questions, feel free to send them to me. Oh, well, no, somebody here. And if anybody came in late, there was at least one person who came in after I checked people in. See me before you leave. Tell me something. Okay, Yang, are you here? Lucas, are you on?
I'm right here.
Lucas is here. Excellent.
Yeah, I have a class just before this. My professor has a lot of time he runs over. Like, so I try and get him to finish my time, but sometimes I'll be there.
Who's the professor?
Walker Rosen. He's a living out.
Okay.
Yeah.
If you tell them that we more than
Yeah, I'm doing the program today, like, the lady has an issue with Zoom and stuff.
okay. That's all right. I don't have to really just say anything. The video's being posted.
Yeah. Thank you.
Jason, are you here? Okay, thank you. All right. All right, I'm stopping Zoom unless anybody has a question. Yes. In the class? Yes, you may. Yeah, no, that should be fine, sure. All right, very good.